In this video with direct variation, we're going to be changing from a graph to an equation and from an equation back to a graph. We talked in the last video about the constant being the same thing as y over x. So today we're going to look more at what this would look like on a graph. If the y goes up and down on a graph, then that means that the y is going to rise. We're going to go up and down. In other words, we're going to rise. And the x-axis goes side to side. Therefore, with the x, we're going to run. And so this term, rise over run, is going to be very frequent. Taking a look at this example, y equals 2x. That's the direct variation equation. And in this example, we see that the constant is 2. So if we turn that into a fraction, 2 over 1, that will again represent rise over run. Now this is different than ordered pairs because when we graph this, we're never going to go back to the origin. We're going to start at the origin to begin with, and then we're going to rise 2. And from that 2, we're going to run 1. We're going to put a new point. From there, we're going to rise 2 more and run 1 more. So we're sort of making stairs, it looks like. We're going to rise 2 more, run 1, rise 2, run 1, rise 2, run 1. And we're going to continue doing this as long as the graph will let us, as many points we have on the coordinate plane. Just like when we were graphing ordered pairs, now that we have points on our coordinate plane, we're going to draw a straight line through these points, making sure we go through the middle of every point. And we notice that the line goes through the origin. And remember, we talked about a line that goes through the origin shows direct variation. So this line on the coordinate plane represents the equation y equals 2x. Here's another example. The equation y equals 7x. The 7 is the constant of proportionality, and we use that as a fraction y over x, which is seen here. And we are going to rise with our numerator. We are going to run with our denominator. And it will look like so. Rise 7, run 1, rise 7 more, run 1. And that's all I can fit on this graph. If I rise 7 more and run 1, I'll be somewhere up here, which is not on the coordinate plane that I'm currently looking at. So all I can have is 2 points. Now I need to draw a straight line through these points. And we notice that as we draw that straight line, once again, we go through the origin, representing direct variation. This equation, once again, is y equals 7x, and that is represented in the graph. Now, as we come to this next example, again, we're focusing on the direct variation equation y equals kx, but in this example, we don't get k. They don't give k to us. They give everything else to us except for k, or except for the constant. So it's up to us to figure out what the constant is. And we're actually going to do this the same way we solve a one-step equation. So as we solve for k, we've got to isolate that variable, isolate the k. And to do that, we're going to divide both sides by 3. Now, once I divide 3 divided by 3, that allows me to cancel those out. And so now what I'm left with is k by itself on the right side and 15 divided by 3 on the left side. Now remember, this is giving us the exact same fraction that we had just previously looked at. So the numerator is our y and the denominator is our x. Now 15 over 3, I could graph that as rise over run, But if I do, I'm going to have to rise 15 and run 3, which is going to only allow me to put 1 point on my graph. So instead, I'm going to simplify 15/3 by 3 and bring that all the way down to 5/1, which allows me to put a few more points on the graph. 5, rise 5, run 1, rise 5 more, run 1 more, rise 5 more, run 1 more, and I'm back at that 15/3 point again. Draw another straight line through all the points, and I now have the graph that represents the equation y equals 5x. And y equals 5x is the same thing as 15 equals k divided by 3. We just had to solve for k and plug it back into the direct variation equation. Another one like that, 108 equals k times 12. And so I've got to divide both sides by 12 so that I can isolate my k. That means that the 12s are going to cancel each other, and k is going to equal 108/12. Now that's my rise over run, but not going to use a graph where I have to rise 108 and run 12. Therefore, I need to simplify. And this page right here shows 108/12 simplifies all the way down to 9/1. So as I go to graph this, it's going to rise 9, run 1, rise 9 more, run 1 more, and I will make a straight line through those points. And again, it goes through the origin. So with my direct variation equation, y equals kx, that is actually y equals 9x for this problem, which is represented by that graph. Let's go the opposite way. Let's go from the graph to the equation. So in this example, I've got ordered pairs or dots already on my coordinate plane. Now, instead of going from my normal ordered pair, which is x and then y, we're going to stay with this rise over run idea. And so how far do I have to rise and how far do I have to run to get to this first point? And that would be I rise 4 and I run 1. Now that means that my k, my constant, is going to be 4/1. And if I plug it into the direct variation equation, it's going to give me y equals, instead of k, we're going to use 4/1, but I don't really need to write that fraction. I could just write the whole number because we know that 4/1 is the same thing as 4. And this is the last example we're going to look at. To get from the origin to this first point, to all the points for that matter, we're going to start at the origin. We're going to rise 1 and we're going to run 2. So that means my rise is 1 and my run is 2, which gives me the constant of 1/2. When I plug it into my direct variation equation, I get y equals, instead of k, I'm going to use that fraction, 1/2 x. And that is how you convert from a equation to a graph or from a graph to an equation.